I'll post it on YouTube after.
Well,
All
I
right.
printed them out, so if anybody needs the answers.
Oh, cool. Yeah, so perfect. You guys can share it too. You can make a Google Drive if you want and share PDFs, whatever. All right. So anything before we start? I don't know how far we'll get, but all right. So, and some of these fill in the blanks are kind of silly. So a function is a relationship between an input quantity and an output quantity. And by quantity, oftentimes you'll say variable. Any synonym of that is okay. So an input quantity and an output quantity, and the input is often called the independent quantity or independent variable, and the output quantity is often called the dependent quantity, or again, variable. All right. And so again, if you've taken math courses before, I'm sure you've all taken math at some point in high school. You'll see like y equals f of x, right? And we'll get to this more in a second, but here y is the dependent, x is the independent. And the reason it's called independent is because you're allowed to, you're changing it, right? You're plugging in different values of x, it's your choice. And the function determines a quantity y. It pops out a function based on the x, right? And so as I said, rewrite function name, input output. So this is just regular function notation, right? So for example, f of x equals y, like I said, where x here, so x equals independent quantity, I'll say variable. Quantity is the same thing. And then y is the dependent variable. And again, quantity. I'm only saying quantity because that's what the book says, I think. All right. Is this legible for all you guys, by the way?
It's kind of blurry for me.
Try to zoom in a little. I got this document camera from JCC, and it worked really well before. I swear, that's what they always say. All right. How's that? It doesn't help that my handwriting's not the best.
That's better. Thank
good?
you.
No problem. All right. The set of values the independent variable takes is called the domain. And the set of values the dependent variable takes is called the range. All right. So for instance, my function f, it maps the domain into the range. Oops, my camera's moving. Just a second here, let me move you over. I'm so confused. All right, we have like camera creep on us. There we go. All right, so it maps the domain into the range. All right, and so what are some examples of functions that you can think of? It can be anything. Give me something. So what about height and age, right? So like, some of these might not be super precise, so maybe I'll say A. So height and age.
That'd be like you shrink as you get older. Or like
yeah, right?
You grow to a certain point, and then you shrink.
Exactly, yeah. So height and age. So age would be your independent variable. And height would be your dependent variable. And again, so this isn't really a precise rule, right? Some people are really tall. It's going to depend entirely on the person. But in general, if you have a child, you can really get a better picture, right? So if you had a child, their graph, well, I guess we'll get to this, but their graph, it would go up, right? I don't want to get too ahead of myself because we're doing graphing in the next section. But in any case, in this case, you'd have f of a equals h, where this, again, a is age, and h is your height. Right? So that's an example, height and age, they're related. What's another one? Any others? I mean, there's like infinitely many. What about What about altitude and temperature? Right? So suppose you're climbing a mountain. And it's got to be a really tall mountain. It can't be like a mountain in New York or anything. It's got to be like Everest. You're climbing a mountain, and as you go up and up, the temperature gets colder and colder, right? And so in this case, my function would relate the altitude to the temperature. So my function would be f of altitude, which I'll call a, equals temperature, which I'll call little t. So altitude, temperature. Right? And so we're not giving like precise relationships between these values. We're just saying that we're just playing around with notation. We're saying these two things are related by some relationship. That's a tautology. And we call that relationship f. And we can vary the altitude, and it pops out different temperatures. So as the altitude in this case, for instance, you're on a mountain, as the altitude increases, your temperature will decrease up into a certain point probably. Right? So just again, just examples. You can make a lot of them, right? But let's continue.
What about a car and water? Would that be an example?
A car and water?
Yeah, like hydroplaning.
Oh, yeah, you could do something with hydroplaning. So like you could say maybe it's like the number of inches of water on the roadway and your chance of hydroplaning. So as the number of inches of water on the roadway increase, your chance of hydroplaning probably also increase. I'm not an expert in hydroplaning, but it's probably, I feel like that's what it is. Maybe like the bolus of your tires. But you could make relationships. Yeah, really about anything you can make relationships.
Yeah, it just popped into my head.
Yeah. On this note with the car, like fuel consumption kind of be that way, like distance.
Exactly.
Fuel used.
Miles per gallon and distance.
I forgot that one.
Mm-hmm.
We actually had that in the last semesters.
Exactly. Yeah. We'll do a lot more of these later. I forget what section that was. Anyway, plugging an input value into a function is called evaluating the function. Right? And we were kind of doing that already. So let's look at a different kind of example. So the two examples we talked about earlier, or the three, I guess, if you count the car, are all very abstract, right? I was talking about like altitude and temperature and like miles per gallon and miles you can drive is very not abstract. But some of them, like height and age, are kind of abstract, depends on the person. But what you can do as well is you can make really precise pictures. So for instance, if I were talking about a domain that looked like the following, suppose my domain consisted of the elements 1, 2, and 3. And suppose my range consisted of the elements 0, 1, right? Right, so these are the two elements in my range. These are the two elements in my domain. And now suppose my function, well, again, we'll call it f, maps my domain to my range, right? So the way you can construct a function, and I'm just making this up, right? We're just making an example. The way you construct this function is you send one element in the domain to one element in the range. So in this case, again, arbitrarily, I can send like 1 to 1. I can send maybe 2 to 0. Maybe I'll also send 3 to 0. Right? And that's a function. We just made it. It's not given by an abstract or like an applicable relationship like we talked about earlier with like height and age or anything. And it's not even given by a formula. It's just given by this cool diagram, right? So if I evaluated f at 3, what's f of 3 going to be?
Would it be 0?
Yep, exactly, because f maps 3 to 0, right? Oh, and I guess let me change this. I'll make it 0, right? So f of 3 equals 0. Now, so that's the first question. Maybe I'll put A, and I'll put B. So B, when does f of x equal 0? So for what values does this function map to 0?
2 and 3.
Yep, 2 and 3, exactly. Right, so is that clear? So it maps 2 to 0, and 3 also maps to 0. So if x equals 2 or 3, then f of x is 0. Right? Any questions about that example? Kind of getting slightly more complicated. We're building. All right. So graphs of functions. So it's almost impossible to talk about graphs or functions without mentioning the graphs, right? So like earlier, I scribbled this out because I wanted to talk about the graph of the function, but we hadn't gotten there. So it's really important. It gives you everything about the function. So to graph a function f, we put the input quantity on the horizontal axis and the output quantity on the vertical axis. Basically, we put the independent, which is oftentimes x, on the horizontal, and we put the dependent, which is oftentimes y, on the vertical. Now, it's not necessarily always x and y. X is not always your independent, y is not always your dependent, but in almost all situations where you have variables x and y in a function f, that's what they are. It's just the standard notation. All right, so let's do an example. And I will give you that this explanation is a little, I don't know, this is not a good explanation, but I didn't want to write it all out. I figured I'd just kind of do an example for you. Let's start by graphing x plus 2, all right? And then we'll do these two parts. All right, I guess I'll get a paper because I'm running out of sheets, right? So my function is f of x equals x plus 2, and I want to graph it. All right, so what you do, in general, what you can do is, a good place to start is by making a little table. Right, so especially if you have no idea what the function looks like, making a table of values and plotting them and then connecting the dots is like a surefire way to get an answer, or to get a graph. In this case, if you've taken a math class before, you probably know this is just a line. So there's a lot of other ways you can sketch this really quick. But if you weren't aware of that, you can just make a table, like I said. So I'll put x values and y values. And I'm going to kind of arbitrarily choose some x values to plug in. There's no right or wrong x values to plug in. You just want to plug in x and y values that you think will give you an idea of what the graph looks like, right? So I'll just do, I don't know, I'll do -2, -1, 0, 1, and 2. Okay? And so now my f of x is my y. And so to get the y coordinate, I just take each x value and evaluate f at that x value, like we just did. So for instance, if I plug in x equals -2 into f, what do I get? Right, so I do f of -2. And so again, you're evaluating the function f at -2. So it's going to be -2 plus 2, right? So what is that?
0.
Yeah. Now what about f of -1? What do I get when I evaluate f at -1?
Positive
Yep.
1.
Exactly, yeah, because it's -1 plus 2. So it's +1, all right? Let's just do, we just got 3 more. F of 0, what is f of 0 going to be?
2.
Yep, because it's going to be 0 plus 2. You can almost see a pattern arising, right? F of 1 is going to be 1 plus 2, which is 3. And then f of 2, of course, is just 2 plus 2, which is 4. All right, so, I mean, the pattern, it's, my y values are 0, 1, 2, 3, and 4. And this goes on, like I said, this is not a finished list. It goes on in both directions infinitely. And there's even, interestingly enough, infinitely many values you can choose between -1 and 2, or between 0 and 1. It's amazing. It's super dense. But this is enough points for us to sketch it. So now, once we've made a table, we plot. Right? So to plot, like I said, what I said over here, right? I put the x on a horizontal axis, and I put the y on a vertical axis. So I put them down. The horizontal is my x, the vertical is my y. The center is 0, right? So the center is 0 in both. And you can make a grid. In this case, since I plotted the points, I plugged in the independent variables -2, -1, 0, 1, and 2. I'll probably put those down. but you can make it as, as detailed as you like. So I'll do 1, 2, minus 1, minus 2. And I should note my spacing is never very precise. It doesn't matter. We're just getting a sketch. If you have graph paper, feel free to use it. And then on the y, I look at my y coordinates, right? And the y values I got were 0, 1, 2, 3, and 4. So when I go to graph these points, I don't really need anything down here because none of my y values were even negative. So what I'm going to do on my axis is I'm just going to put 1, 2, 3, and 4, right? And that's my, I have a grid set up, I have my axes set up, and now I'm ready to plot. So the way we plot the points is you, for every x coordinate on our table, you go to that point. So x is -2, I go down here at -2. And at -2, I got y equals 0. So I go to -2 on the x, and then I just evaluate, I put a dot at 0. Does that make sense? So if you want, you can write it like a coordinate. So as a coordinate, and a coordinate is just a pair. It's an xy pair. So for instance, I get -2, 0. So this is xy. I get -2, 0. For this one, I get -1, 1. For this one, I get 0, 2. For this one, I get 1, 3. And finally, for this one, I get 2, 4, right? And so basically, we're just going to plot these 5 points on our grid, right? Where again, the first coordinate is the x, and the second coordinate is the y. So again, so -1, 1. I go down to -1 in the x, put a 1 on there. Oops, off my paper. Sorry about that. The next one's 0, 2. So I go to x equals 0, which is right here. Go up to 2, plot a point in there. The next one is 1, 3. I go to 1 on the x, go up to 3 in the y, plot a point in there. And then finally, the last one is 2, 4. So I go over to x equals 2, up to y equals 4, and plot a point. And it doesn't look like much, right? We've only plotted 5 points, but if you connect the dots, you're good to go. So you just do like a little, if you have a ruler, this is obviously better, but there you go. You connect the dots, and that's my line. So connect the dots. Sometimes connecting the dots is easier than others. And you do want to label it. In this case, we only graphed one function, but it's always nice to label what the function is. All right, so any questions about plotting? Just like kind of quick, something to jog your memory. All right. And so if you recall back to the example we were doing, it said to first graph the function. We did that. And the next part, it said, what is f of 3? So in this case, so f of 3. So f of 3 is not on our graph, right? It doesn't have to be, though, because what we can do is we can just plug it in. So what is f of 3 going to be?
5.
Yep. So that's easy. And if you wanted to, of course, you could just plot it. It'd be up there. All right. Second question. When does f of x equal 6?
At f of 4?
4.
Yeah, exactly. Right? It's just 4. So the way you would do that, so you can do it by observation, right? That's probably the way most people would do it for a function that's just x plus 2. So you're asking yourself, when does 6 equal x plus 2? Obviously, 2 plus 4 equals 6, and so x equals 4. But the other way you could do it would be to, so you have f of x equals 6, right? And so this kind of, we're going to do a lot of this, like solving algebraic equations. We're not going to do anything as complicated as you would do like in a pre-calc course, but we're still going to need this kind of ability. So this is a good introduction to it. The next thing you do is you sub in f of x equals x plus 2, right? So I plug that in here. So I get x plus 2 equals 6. And then you just solve for x by subtracting 2 from both sides. So x plus 2 minus 2 equals 6 minus 2. And so x is just equal to 4. Right? So that is a very very explicit solving for x equals 4. Most of you probably don't need it, but it's good to see it. Alrighty, so that's that example. Let's do one more graph, because graphing will be important. This one I have room for. We might skip some of these parts, but let's at least graph these two functions and move on, right? So the next one looks similar. And again, if you remember anything from any math course you've taken in high school, this is going to be a line. But what's interesting is that it has a negative sign in front of the x. So that's going to do something special, right? So let's do the same process we did. Let's make a table, x and y. And let's just plot some points. This time, maybe I'll do 0, 1, 2, 3, 4. There's no right. As long, for strictly speaking, if you're graphing a line, you just need to plot 2 points, but we'll do more, right? So again, y equals f of x. So y equals f of x. And so to get the y coordinate for each of these x coordinates or independent quantities, as I called them earlier, you would just evaluate the function f at the respective one. So what is f of 0 going to be here?
That'd be negative
1.
3.
Careful. Yeah, it's 1, right? So if you plug it in, you get minus 3 times 0 plus 1. And so 0 times minus 3 will be just 1. Yeah, so I get 0 plus 1, which is 1. Cool. All right, the next one, f of 1. So again, you plug it in. So minus 3 times 1 plus 1. And so now you just need to do some computation. So minus 3 times 1 is minus 3. And then plus 1 is what?
-2.
Yep. Oh, and I should note, I didn't think I mentioned earlier, I don't think we'll need like a scientific calculator like this or anything. But if you have one, obviously you can use it unless I say otherwise. Some of the things will be like on the test will be like graph this, graph that. So in that case, I probably won't want you using a graphing calculator. But for the homework and anything else, feel free to use a graphing calculator. You will be able to use a scientific calculator for anything. A scientific one, I don't think I have one around here, but a scientific one just doesn't have a big screen on it. So, and they're cheaper. They're like $10 at Rite Aid. Right. Anyway, f of 2. What's f of 2? See, so minus
-5.
Yeah, exactly. So minus 3 times 2 plus 1. So minus 3 times 2 is minus 6. Plus 1 is minus 5. All right. F of 3. Minus 3 times 3 plus 1. Let's see. So that's minus 9 plus 1. Minus 8. Alrighty. And then the last 4. Minus 3 times 4 plus 1. So let's see. Minus 12 plus 1 is minus 11. All right, and you might be able to see a pattern here kind of arising, right? You started at 1, minus 2, minus 5, minus 8, minus 11. So if you look, you'll notice that it's decreasing by 3 each time I increase my x value by 1, right? So we'll get to that probably, I don't know, actually next class. But anyway, to graph this now, if I have room, I took up a lot of room making a graph. You just plot the points like before. So again, I have x on the horizontal, I have y on the vertical. And I'll just make notes where my x values are that I want. So 0 is here, 1, 2, 3, 4. Again, my spacing is never good. You should always use a pencil when you're doing math. It's always a good idea to use a pencil. And then for the vertical, I look at my values and I have 1, I have minus 2, I have minus 5, minus 8, minus 11. So really, I should have made it lower like this because the highest I have is 1. So at 0, I'm 1. And then as I go to the right, my values are going to decrease, right? So at 1, I'm minus 2. So I'll put that there. At 2, I'm minus 5. Right, I'm there. 3, I'm minus 8. And then minus 11. I'm kind of going down the page here. Right, so 3, I'm minus 8. And then 4 minus 11. So if I connect the dots on this one, again, since my scale is a little off, the dots are going to be a little off, but it's going to look something like this. Right, and that's basically my line. It's a nice little sketch. So f of x equals minus 3x plus 1. Right? So make it as neat as you like. The neater, the better. All right, any questions with that? So compare and contrast with the one we just did, right? So where'd it go? This one, my function, so the way I can look at this, right, is I can say this is f of x equals 1 times x plus 2, right? So the way you can interpret it is all it's saying is that for every time I increase the x coordinate or the independent variable by 1 unit, I add 1 to the whole expression, right? So I go over from 1 to 2, I go up by 1. I go over from 2 to 3, I go up by 1. Right? And it's the same kind of operation here, except now every time I go over 1 on the x coordinate, I go down 3 on the y. Right? So this is, when we do a little more about lines, this is called the slope. And it tells you the rate of change of your function. Right? Again, everyone's probably heard of the slope, so it shouldn't be too unfamiliar. But anyway, I'll skip these next two. You can give those a go. They're just like the ones before. But let's grab this one. This one's a little more interesting. All right, this is my favorite function probably, at least in like a math algebra sense. And you can do so many great things with it, but we're gonna graph it just like before. So oops, let me make a little line, x, y. Try to save more space for my grid. There we go. All right, so x, y. All right, and let's make a little table. This one, I'll just, it doesn't really matter. You can do either side, but I'll just do kind of in the middle so I have a good idea of what the whole function looks like again. So I'll do -2, -1, 0, 1, 2. Okay. Let's plug it in. So again, y equals f of x. And I should note, so like here I said just graph f of x equals x squared, and I didn't tell you what the y was. So if you're ever told to graph a function, the assumption is that the function itself is that independent or that dependent variable. So here, if I just say graph f of x equals x squared, I'm really saying y equals f of x, graph the y or the function as the dependent variable on the vertical. All right, but let's do it. So let's plug it in. F of -2, what is f of -2 here?
I mean, -4.
Careful, it's 4, it's positive 4, right? So what happens is you have -2 times -2. And so what happens when you multiply a negative and a negative?
Becomes positive.
It's positive, yeah. So the negatives cancel and I just get +4. All right. What about f of -1? What happens there?
It becomes positive.
Mm-hmm. Yep, exactly. So for the same reason, right? I get -1 times -1, which becomes +1 because the minuses cancel with each other. And I just get 1 times 1, which is 1. What about f of 0?
0.
Yep, because 0 times 0 is itself 0. F of +1 now?
1.
Mm-hmm. And then finally f of +2.
4.
Beautiful. Right? So it's just such a beautiful function, right? Like it goes 4, 1, it's symmetric. And you can play as many points as you do around 0. As you compute around 0, you'll see that the negative version is exactly the same. And that's just because of the reason I mentioned earlier, right? When you multiply a negative times a negative, it'll cancel. And so f of -x is the same as f of x here. And that gets into something we'll do later about transformations. But for now, just kind of observe that there's some symmetry going on. But let's plot. So 2, 1, 0, 1, 2. And again, make your plots prettier than mine. I plot -2 at 4. So it's up here. And you can even, I should make a grid. 1, 2, 3, 1, 2, 3. There you go. So at 2, it's 4. At -1, it's 1. So -1 is here, so it's up to 1. 0 at 0, so it's right at the origin. At 1, my y is 1, so I go over to x equals 1, and I plug in y equals 1, or I put a dot at y equals 1. At 2, it's 4 again. So at x equals 2, I go up to 4. And now you just connect the dots. And this one, you might not know what to do, right? Because it's certainly not a line. If it's a line, it would have to look like that or like that, and it doesn't really work. But if you just connect dots, like I said, you'll get what's called a parabola. And strictly speaking, this is called a quadratic. That function x squared is called a quadratic, and its graph is this lovely little parabola. And there you go. And it extends infinitely in both directions. As you go out on the x-axis towards the right or the left, it's going to go up towards infinity in both directions. It's kind of fun. Right. Any questions so far?
So 0 would be the lowest point of always, like.
Yeah. Yeah, so this function can't get any lower than 0, which is an observation that you actually use a lot in, I don't know, I remember I taught calc the one year, and it would always come up. Like we'd be doing something, and I'd always have to remind students that x squared was positive, like greater than 0. Like the smallest it could be was 0. So it's a good observation. Yeah, the smallest it can get is 0. It can never be negative. And yeah, and so the only time it would be negative is if you were dealing with imaginary numbers. And we don't deal with imaginary numbers right now. I think they're in a later chapter, but not something we're going to handle. All right, any other questions? All right, behavior of functions. And I've been talking about this a little bit, but it's sometimes not clear what an increasing or a decreasing function is to some people. So I wanted to make it really explicit. So as we go from left to right, so inputs are increasing, a function is increasing if the outputs get larger. It's decreasing if the outputs get smaller, and it's constant if the outputs do not change. Right, so for example, in these couple that we just did, this first one, again, so it's, let me try to fit it all. It's from, as you go from left to right on the graph, so the inputs are increasing. So the inputs, remember, in a lot of these cases are the x values, and the outputs are the y values. So as the x values increase, the function's increasing if the y values get larger, it's decreasing if the y values get smaller, and it's constant if the y values do not change. So in this first case, or in the second case we did here, with minus 3x plus 1, as I go from left to right, this direction, my y values get smaller, right? As I go to the right, like I said, from the left, my y values are going to decrease. They're going more and more negative, and I'm decreasing by 3 each time. Right? Now, this function, this quadratic that I mentioned a minute ago, this function is completely different, right? So this function, again, I'm going left to right, so I'm reading it that way, kind of like you read a book. And as I go from left to right, my function, my y values are decreasing. And you hit 0, and the y values start increasing again. So this function is decreasing here. Oops, I can't spell decreasing. And they're increasing from 0 to infinity. There we go, sorry. So that if I put my pen in the middle, on this side, they're increasing. On this side, they're decreasing. And it's not neither of these functions are constant anywhere. So to look at a constant function, we can check out this one, right? So let's see, let's graph it and see what it looks like. Y, x. Does anyone have any guesses as to what the graph of f of x equals 4 is going to look like?
A straight line across, because y always equals 4.
Exactly, yeah. It's just a flat line across because every x value you plug in, you just get 4, right? So if I plug in 0, I get 4. If I plug in 1, I get 4. Like there's no x at all in the expression. It's just straight 4. So for all these values, it's just 4. So it's constant. And you'll note, again, as you go from left to right, the y values do not change. They're just 4 the entire way. Right. And then these two, we can probably guess, right, based on what I was talking about a minute ago. So this one, this is a line, right? And as x increases, what's going to happen to y? So y here, you can think of it as y equals minus x plus 1, right? So as my x values increase, what's going to happen to the y values?
It's gonna decrease.
Exactly, yeah. So as my x values increase, you can also, if you wanted to, you could graph this function as well to see exactly what it looks like. But I just wanted to show you a kind of different way of analyzing the situation. So as x values increase, x values increase, y values decrease, right? And it's just because of that negative. It's all because of that negative in front of the x. So as you put higher and higher numbers in for x, those are going to be bigger and bigger negative numbers that you're then adding 1 to. And so they're still going to get bigger and bigger and more negative, even though you're adding that 1. Right? And for the same reason here, because of this positive 2, as x values increase, and again, so by saying that x values increase, I'm saying we're going from left to right on the graph. The y values increase. All right. So as x, for every x you go up. So if I go from x equals 1 to x equals 2, the difference in the y, which is again the function, is 2, because I'm basically just adding 2 every time I increase the x by 1 unit. So for instance, if I start at 0, I get 5. If I plug in 1 for x, I get 7. If I plug in 2, I get 9. If I plug in 3, I get 11, and so on and so forth. You just keep adding 2 every time, right? And so just to be clear, this one's increasing. This one's decreasing. And this one's constant. Okay. And again, because I said you could have graphed those just like I graphed the other 2 a second ago. All right, anything? Any problems so far? Cool. And so again, the reason we're doing so much about like functions is because we're setting ourselves up to study linear and exponential growth, which is a little more interesting. But maybe we'll end here today. I don't want to do too many, and it's already 2:20, so I figure we'll end a few minutes early. If you have any questions, shoot me an email. So between now and Thursday, what I want you to do, wait, let me share screen. Let me stop recording.